and more to push. When you finally reach equilibrium, that's the hardest you're pushing horizontally in the whole motion. So the force is variable in order to achieve this goal of a resting endpoint. You just start from zero, crescendoing up to this maximum F, which we found. Total nonsense to multiply 5 times 1920, because it's not a constant force. At least not consistent with the data which we're given. But that's a subtle point. If they told you, you apply a constant force horizontally as the pendulum swings up, that would be a different problem. It wouldn't be at rest at the end. And then that would be the work done. Yep. What is the work done? Just this right here. It's this one. But in order to find it by integration, I would have to solve the equilibrium problem at an arbitrary point, like assuming it's moving at constant motion, right? I would have to solve the equilibrium problem at arbitrary points along here, and then integrate that. And no, I shouldn't do that. I mean, it's just far easier to say, well, at the end of the day, if you're at rest at the end, then what you've done is you've just added potential energy, but not kinetic energy. So I can just look at the change in potential energy, and that'll give it to me. Sorry. I like it when the problem makes me think something incorrect. All right, I digress. Where are we? Okay, in the time that remains, I need to show you a couple things. I like my sticker, but I don't have a lot of hope these days. These are dark days. Yeah, I don't know. Well, I know. We'll see. We'll see. Yeah, he's probably. I don't know. I guess if somebody was like, he should come out in the debate and just call Trump a bunch of names and see what sticks. I hope he takes that advice. I like uncivil debates. Yes. What's that? Ah, yes. Yeah, he should take Texas at least. That is true. All right. Where am I? Oh, yes. Woo, this thing moves. So what I wanted to show you guys was just a careful derivation of the case of the non-conservative case. Well, reasonably careful. Oh. All right. So I usually work through these problems carefully, but I think I've used time to work through WebAssign problems instead of. Forgive me for that. I hope. Let me find my laser. All right, so here's sort of a generic discussion. Suppose, well, what about friction? All right. What about, whoa, oops. Forgot my diffracting thing. There we go. Woo. If the net force is a conservative force plus a non-conservative force, the conservative force has a potential energy function associated with it, but the non-conservative does not. All right. And so we don't really have any expectation that the energy, which is 1/2 mv squared, plus the potential energy should be conserved. All right. It can change because of this non-conservative force. And here's how that goes. So you calculate the net work. The net work is remember the work energy theorem is general. So this will always calculate the change in kinetic energy. That's a generic fact of our calculus. But the net force now has two pieces. It's got the piece from the conservative force, and it's got this other piece from the non-conservative force. That could be friction or something else. It could be, me pushing on stuff, like so. And then, you've got, on the one hand, the change in potential energy, but you've also got the work done by the non-conservative force. And so the conservation of energy is modified to this, which I can rewrite in a more useful form down here. Basically, here's the deal. The energy at time 1 is equal to the energy at time 0 plus the work done by the non-conservative force. That's either negative or positive depending on whether it's like a friction or it's like you kicking the soccer ball and adding energy to the system, And so that's the modified truth. We have to either add or subtract energy as accounted for by the non-conservative force. So here's an example. I started with example 1, how far does the box slide up the incline? We did that a few days ago, all right, that one. Now what if there's friction? Well, what happens is, in order for once it slides up so far, the force of friction, of course, takes away kinetic energy, right? Energy's lost to friction. You've got some kind of pesky, you have to relate h to d and sine theta. There's trigonometry hiding in this problem as usual. So, long story short, the work done by friction is the force of friction, which is this guy, times d, which works out to h over sine theta. And so my final energy would be mgh, right before, when the box comes to an end, comes to a rest at the end of the sliding up the inclined plane with friction. The initial energy was kinetic, and then you've lost this much due to friction. And so that gives you, and then you can solve for h. And there you go. Don't get too hopeful that this is a formula you could just copy onto a card and use without explaining. But there it is. And of course, it's fun to think about special cases. For example, when mu is equal to 0, we get v naught squared over 2g, which is what we found before. Another example, if you just push with a horizontal force, horizontal to the ground or horizontal to the plane? I'm not sure with my wording. Oh, apparently horizontal to the ground, right? See? So that's not directly in the motions. Part of that is, well, I don't know. What does that do? Well, if there's friction, is there friction? Oh, anyway, I'm out of time. I'll shut up. I wanted to share with you, what happens if you have a non-conservative force in there. Uh-oh. Oh no. Oh. It's over there.